Okay, so I changed my mind. I'm not going to draw a new system. This one's perfectly good. So I was talking about the concept of heat. So heat is a word that implies energy in motion, energy flowing, transferring, moving from a place where there's higher temperature, that is to say higher average kinetic energy per particle, to a location that has a lower temperature, lower average kinetic energy per particle. Hot coffee down to out to the cooler air. Okay, and then I said, having defined heat, then I did the first law of thermodynamics, which simply said that when you change the total thermal energy of a system, there's only two ways to do that: is to either have work happen in or by, on or by the system, and the other way to change the thermal energy that a system has is to either allow energy to flow into or out of the system. And the first law of thermodynamics says that the amount by which that internal thermal energy of the system changes is equal to the sum of those two things. Okay, which seems reasonable enough. And as I mentioned before, that's really just an expression of or an application of conservation of energy, and that's fine. And then I hinted that there's another law, for peculiarly not called the first law, but the zeroth law, and what's going on there. All right, well, let's take another look at this. I discussed earlier, a couple of recordings ago, I think, that this flow of energy, this heat, will continue to happen as long as there's a difference in the thermal energy of the coffee versus the thermal energy of the surrounding air. Once the average energy per particle, which is equivalent to saying, once the average temperature, once the temperature of the coffee is the same as the temperature of the air, their energies per particle are equal. There's no longer any cause of energy transfer, and so the net transfer of energy becomes zero, the heat becomes zero, and now we have a new vocabulary term. And so here we go. So when Q is equal to zero, the system is, this is said to be, this is how we describe it, said to be in thermal equilibrium. With its surroundings. So thermal equilibrium, that's the new vocabulary term. Thermal equilibrium simply means that the system and the surroundings are at the same temperature, which again implies that they have the same average kinetic energy per particle. And I keep emphasizing that because we're going to eventually discuss the difference between the average kinetic energy per particle versus the total amount of energy contained in the system. Those are related, but they are very different from each other. In any case, now, let me, I guess I'll come over here. Let me discuss another situation with you. I have to erase this drawing here. I never did, by the way, tell you the other system of units for temperature, but there's a reason I didn't. But I will get to it eventually. Okay, so now I'll go with my simplified model. Suppose I have two blocks. And this one is made of whatever it's made of. And I'll have a second block here. Okay. Made of whatever that's made of. And then perhaps a third block. Apparently I can't draw. I don't know what that is. I don't even know what that is. Okay, it doesn't matter. And let's assume that this thing is solid, something or other. I'm going to assume it's solid because that will hide my mistakes. Great. Okay, so whatever this is, I don't know. Okay, screw it. So I have three different objects. And let's suppose that object one is at, let's be definite here, let's say it's at 10 degrees. Okay. Now, and let's suppose that object two here is, well, actually, I went to all the trouble of drawing it. I think I'll erase it. Let's say object two here is now at 5 degrees. Okay. So this means that object two is at a lower temperature than object one, which means that it has lower average kinetic energy per particle, which means that there's going to be a flow of heat from object one into object two. Okay, so I have flow of heat there. And actually, let me label these objects A and B. Okay. And if I leave them in contact long enough, for reasons that I described earlier and won't repeat, eventually the two objects will end up being at the same temperature. They'll end up in thermal equilibrium. Now, exactly what that intermediate temperature is not obvious from anything that I've said, because after all, the things could be made of different materials, different masses, different kinetic energies, and blah, 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 blah. But whatever, eventually they will come to the same temperature, because saying that they're the same temperature is entirely equivalent to saying that the average kinetic energy per particle of each object is the same. So they will come into thermal equilibrium sooner or later. How long it takes is not my issue right now. What the actual final shared temperature is, not my issue right now. The only thing I care about at the moment is that keep them in physical contact long enough, and they will eventually reach thermal equilibrium. They will eventually be at the same temperature. Okay. Now let's go ahead and add my, well, let's do this. So, and I don't know how you're going to do this on your notes, but whatever. I'm sorry. Anyway, so let's I'm going to choose a random number. This is entirely a guess. Let's suppose that the intermediate temperature ends up being 6.25 degrees. I don't know. Just making numbers up here. Okay, so they end up at the same internal energy. Now, suppose I do bring in my third object, more usefully drawn this time. Okay, and I'll call it object C. Okay, made of something. So I don't know, the first one is made of metal, the second one is made of glass, this one's made of plastic or something. And let's suppose that object C started out at 80 degrees. No, let's not say, let's say 20 degrees initially. Okay. Now, what's going to happen? It is in object C is in physical contact with B, so there will be a flow of energy from C into B. Okay, and as you can see, C and B, that will cause object C's temperature to decrease, object B's temperature to increase. But if object B's temperature increases, that throws it out of equilibrium with object A, which means that now the flow of energy, the heat will be, the direction of the heat will be reversed. And so we'll get a flow of energy this way, QB to A here, QC to B here, okay? And I'm not going to labor the point. Eventually, though, the flows of energy will go back and forth, and eventually all three of them will be in thermal equilibrium. B and C will be in thermal equilibrium. A and B will be in thermal equilibrium. And now here comes the 0th law of thermodynamics. And it simply says that if A and B are in thermal equilibrium with each other, and if B and C are also in thermal equilibrium with each other, then automatically, the 0th law says, it must be true that A and C are likewise in thermal equilibrium with each other. At the end of the day, these numbers might be, and again, I'm just making up numbers here, but these numbers might be 14.2 degrees C. They're all going to be at the same temperature, whatever that is. Okay? And so, but it goes like this. Now I'll come back over here. So the 0th law. There it is. All right. If A is equal to B and B is equal to C, then A is equal to C. This may seem dead obvious, but the fact is it isn't, because notice, if you will, what's missing from this statement. What's missing from this statement is any reference to the sizes of the objects, to the shapes of the objects, to what the objects are made of, whether the objects are solid, liquid, or gas, or indeed any details at all about any of the three objects. Which, the more you think about it, the less plausible that sounds, and yet it turns out to be true. And this, therefore, is an extraordinarily broad statement about the universe as a whole. And the applicability of the 0th law has been extended to and is a very powerful tool for things as disparate as the interior of the nucleus of an atom to the interior of galaxies and the interior of stars. It's an astonishingly powerful and important statement. As obvious as it seems on the surface, it really is not. So I encourage you to spend some time thinking about the significance of this. Okay. The reason, by the way, historically it's called the 0th law instead of the 1st law is because through most of the development of the theory of thermodynamics, there were only 2 laws. The 1st law, which I've told you, and then the 2nd law, which I will get to eventually. And then some, like about 10 years after the first and second law had been stated, it was a physicist, an English physicist named Lord Kelvin, pointed out that throughout all the development of thermodynamics, we had been making this assumption, or they had been making this assumption without saying that, they were making the assumption that this relationship was true without anyone ever actually saying out loud that they were in fact making this assumption. And you might be able to get away with that in politics or English grammar, but you can't get away with that in science. You've got to explicitly tell the world what your assumptions are, okay? Because it's when your assumptions fail, that's when you discover new physics. So we have to know what your assumptions are. But this one, we are sure of. Anything can be, proved wrong tomorrow, but this thing is as certain as anything can be. So there's that. All right, so that's the 0th law, then the first law. The second law will come eventually, not anytime real soon, but we'll get to it eventually. And so that's what that is. And so thermal equilibrium, the 0th law, that'll be good. All right, so we're finally in a position now that we've sort of laid the groundwork for everything, we can start examining physical systems specifically and start being able to do calculations about how these systems change when you change the amount of energy that they have, and also make some calculations. How do you go about changing the internal energy, the thermal energy of a system in the first place? The first law gives you a hint, but we need to put that into practice. So that'll be in the next upcoming lectures. We'll look forward to that.